Hey everyone, and welcome to another deep dive. This time, we're going to be looking at magnetism and electromagnetism.
Oh, yeah.
Two really important topics for GCSE physics.
Definitely. Some really interesting concepts and some practical applications as well.
Absolutely, and I think for a lot of people, when they think about physics, they kind of think like, oh no,
Yeah.
these like equations and symbols and things like that. But I promise you, these two topics are actually really fascinating.
Yeah, they're quite cool. Magnets are cool anyway, right?
They're really cool. It's kind of like magic when you think about it.
Yeah.
So speaking of cool, we've got a very cool expert with us today who's going to be guiding us through all of these ideas and concepts and, really helping us to kind of wrap our heads around them.
Yeah. I mean, we all played with magnets as a kid. I think it's one of those things you always remember.
Yeah.
Just playing with them and seeing how they attract or repel and stuff.
Yeah. So I guess let's start then with those classic bar magnets.
Yeah.
That I think we've all seen at some point. The ones that you might have on your fridge or even just in a science classroom.
Yep. Yeah.
The ones that they've got the North Pole and the South Pole clearly marked on them.
Yeah, and you can get them to stick together or push each other apart, can't you?
Yeah. And that's always fascinated me as a kid. Like, why did they do that?
Yeah, well, that's the simple rule, isn't it? So opposites attract and like poles repel. So, if you try and push two North Poles together or two South Poles together, they just won't go near each other.
Yeah, it's like there's an invisible force field between them.
Yeah, exactly. Yeah. So that's all to do with the magnetic field. So that's the kind of the area around the magnet where the magnetic force can be felt.
Oh, okay. So it's like this invisible sort of aura around the magnet.
Yeah, exactly. And you can represent that,
Yeah.
if you've seen diagrams with magnetic field lines. So they always go from north to south, and they kind of show the direction of that force. And just like with any force, the further you go away, the weaker it gets.
Okay, so the closer you are to the magnet, the stronger that pull or push is going to be.
Absolutely, yeah.
So it's kind of like, I guess, when you're at a gig and you're standing right next to a speaker.
Yeah.
Versus like being, way at the back of the venue.
Yeah. The sound's more intense, isn't it, when you're up close?
Yeah, exactly. So it's kind of, a similar idea.
Yeah, and just like sound waves affect your eardrums, the magnetic fields can affect certain materials. Like if you've ever seen iron filings, that's always a good experiment in school, isn't it?
Oh, yeah, I remember doing that.
And they just sort of magically line up, don't they?
Yeah.
It's like seeing the invisible visible.
Yeah, it's amazing. It is. It's like you can actually see the force field.
Yeah.
That's so cool. But I'm curious, like, are all magnets the same strength?
That's a good question.
Because, I'm thinking like the magnet on my fridge that's holding up, a postcard versus like those huge magnets that they use to lift cars in junkyards.
Yeah.
Surely they can't be the same strength.
Well, no, they're not.
Right.
Because there's different types of magnets, just like you get, different types of batteries.
Right.
With different power, you get different types of magnets. So you've got your permanent magnets, which are the ones that are always magnetic.
Yeah.
So those are the ones on your fridge.
Okay.
And then you've got what are called induced magnets, which are only temporarily magnetic.
Induced magnets.
Yeah.
That sounds a bit more complicated.
I guess so. Think of them as being a bit shy, so they only show their magnetic personality when they're near a permanent magnet. So if you imagine a paperclip, for example,
Right.
That's not magnetic on its own, is it?
No.
But if you bring a magnet close, suddenly it sticks to it, so it's become a temporary magnet.
So it's like the permanent magnet is giving it like a temporary magnetic boost.
Yeah, exactly that.
I like that. A magnetic boost, yeah.
Yeah.
But I guess not every material can become an induced magnet, though.
No, you're right.
Like, I can't just, like, magnetize my pencil.
Well, you can try,
Yeah.
but it won't work.
Yeah.
It's only certain materials like iron, nickel, and cobalt.
Okay.
They've got this kind of hidden magnetic potential.
So it's all to do with, like, their atomic structure and all that kind of stuff.
It is, yeah.
Wow. Okay, so we've got these permanent magnets, these temporary induced magnets.
Yeah.
Are there any, like, truly massive magnets out there? Like planet-sized magnets?
Well, funny you should say that. Because planet Earth
Uh-huh.
is a giant magnet.
Wait, are you serious? Our whole planet
Yeah.
is one big magnet?
It is, yeah.
That's insane.
It's all thanks to the Earth's core. So you've got this molten iron core
Right.
right deep down inside the Earth.
Yeah.
And that's constantly moving. And it's creating this huge magnetic field that surrounds the planet.
So that's why compasses work, right?
Right, yeah.
Because the needle is basically aligning itself with the Earth's magnetic field
Exactly.
to point north.
It is, yeah. Although there is a slight twist, you see, because the Earth's magnetic North Pole is actually a magnetic South Pole.
Wait, what?
Yeah.
How can the North Pole be a South Pole?
I know, it's a bit confusing, but that's how it works, because remember, opposites attract.
Right.
So the north end of your compass needle is attracted to the Earth's magnetic South Pole, which just so happens to be located near the Earth's geographic North Pole.
Okay. My brain is officially doing a loop-the-loop right now.
Yeah.
But I'm kind of starting to see how it all fits together.
Yeah.
We've got these magnets, we've got these magnetic fields, we've even got our whole planet acting like a giant magnet.
Yeah.
Is there any connection between all of this and electricity, though?
Well, that's a great question. Because, yeah, there is. The two are they're like best mates, really.
Yeah.
They're inseparable. So when electricity flows through a wire, it creates a magnetic field around that wire.
Seriously. So
Yeah.
every time I plug in my phone charger, I'm creating like this invisible magnetic field.
You are, yeah. And you can work out which way that field goes using what's called the right-hand grip rule. So if you imagine grabbing the wire with your right hand
Okay, yeah.
and your thumb's pointing in the direction the electricity's flowing,
Right.
your fingers will naturally curl around the wire, and that shows you the direction the field lines go.
So it's like my hand is a compass for the magnetic field.
Exactly.
That's pretty neat. I like that.
But
I'm guessing the strength of the magnetic field depends on how much electricity is flowing, right?
yeah, absolutely.
Right.
So the higher the current, the stronger the magnetic field's going to be.
Okay, so more electricity equals a stronger magnetic field.
Yeah, that's right. Yeah.
But is there any way to make those magnetic fields even stronger? Like, can we supercharge them?
We can. That's where things called solenoids come in.
Solenoids.
Yeah.
What are those?
Well, solenoid is basically a wire that's been coiled up.
So instead of having, like, a straight wire,
Right.
we've wrapped it around and around.
Yeah, exactly. Like a spring.
Okay, and what's the benefit of doing that?
Well, if you imagine when you coil it up, you're concentrating those magnetic field lines.
Oh, okay.
So the field gets a lot stronger than it would be from just a single wire.
Oh, okay. So it's like we're bunching all of that magnetic power together.
Yeah, exactly. And you know what? The field around a solenoid starts to look a lot like the field around a bar magnet.
Oh, wow. Really?
Yeah.
So we can basically create like a magnet-like field just by coiling up a wire.
Yeah, absolutely.
But can we make it even stronger?
We can. So if you put something called an iron core inside the solenoid,
Okay.
that makes the field even stronger.
Why iron? What's so special about iron?
Well, iron's really good at conducting magnetic fields, so it kind of acts like, a superhighway for the magnetic force.
Right. So it's like it's amplifying it.
Yes.
This is pretty amazing stuff. So I'm guessing these solenoids aren't just like a cool science experiment, though, are they? They must have like some real-world uses.
Oh, loads of uses, yeah.
Right.
Yeah, so you find them in things like doorbells, you find them in speakers, even things like electromagnetic locks. So, if you go through like an electric gate or a door,
Oh, right. Yeah.
that's using a solenoid. And you know what else they're using? MRI machines.
MRI machines, those huge scanners you find in hospitals.
Yeah.
What do solenoids have to do with those?
Well, they're used to create those really, really strong magnetic fields that you need to generate those detailed images of the inside of your body.
Wow, I never would have thought of that.
Yeah, they're pretty powerful.
So it's like seeing right through you, but without using like X-rays.
Yeah, exactly that. Yeah.
Wow, that's incredible. I never realized magnets were so important in all this high-tech stuff.
Yeah.
This is pretty mind-blowing. But it gets even more interesting when we start looking at how we can use these magnetic fields to actually create motion. Wait, you mean we can use magnets to actually make things move?
Yeah.
Really?
Yeah. That's called the motor effect.
The motor effect.
And that's kind of the principle behind how electric motors work.
Okay, now we're talking.
Mm-hmm.
This is where things start to get really interesting.
Yeah, we'll get into that next time.
All right, I'm ready. I can't wait.
Yeah.
Lead the way. This is electrifying stuff.
It is. I love it. Great. So before we got a bit sidetracked by solenoids and MRI machines, we were talking about how magnets and electricity are best mates.
Yeah, exactly. And you were about to tell us how that leads to things actually moving
Yep.
with this thing called the motor effect.
That's right, yeah. So basically, if you've got a wire that's carrying electricity and you put it inside a magnetic field,
Okay, yeah.
like the one from a bar magnet, that wire is going to experience a force.
Wait a minute. You're telling me just by putting a live wire near a magnet, it'll actually move?
Yeah, it will. It'll move.
That's crazy.
Yeah, that's the motor effect. So the magnetic field from the magnets interacting with the magnetic field created by the current in the wire, and you get movement.
So we're literally talking about turning electricity into motion here.
Yeah, absolutely.
That's pretty amazing. But is there any way to figure out like which way the wire will move?
Yeah, there is.
Like, will it jump up? Will it jump down? Will it move sideways?
Well, there's a handy little trick called Fleming's left-hand rule.
Fleming's left-hand rule. Okay,
Yeah,
no.
this is your secret decoder for the motor effect.
All right. I'm all ears. Tell me how this works.
Okay, so stick out your left hand
Okay.
with your thumb, your index finger, and your middle finger all pointing outwards, like you're doing a really awkward high five.
All right, I think I've got it. Looking very stylish here. What do those fingers actually represent then?
Okay, so your index finger, that points in the direction of the magnetic field, so from north to south of a magnet.
Right.
Your middle finger points in the direction the electricity is flowing, so in the wire.
Yeah.
And your thumb points in the direction that the wire is going to move.
So if I know where the magnetic field is and which way the electricity is going, I can use my hand to predict how the wire is going to move.
Exactly that, yeah.
That's amazing.
Yeah, and just like we were talking about with the magnetic field around a single wire, the strength of this force in the motor effect depends on a few things. So a stronger magnetic field means a stronger force, and more current flowing through the wire also means a stronger force.
Okay, so it's all about power. Stronger magnet, more electricity, more oomph.
Exactly, yeah.
But how does all this translate into an actual motor then? I mean, I've seen motors like, they're not just wires dangling next to magnets.
Well, no, let's think of something simple, like an electric fan. So inside the fan motor, you've got a permanent magnet that's creating that magnetic field, and then you've got a coil of wire,
Yeah.
which is kind of like a solenoid
Right.
mounted on an axle so it can spin.
So the wire is like a little merry-go-round inside the motor.
Yeah, that's a great way to put it.
I like that. Okay.
So when you switch the fan on, electricity flows through that coil of wire, creates its own magnetic field, interacts with the permanent magnet's field.
Right.
And that produces a force that makes the coil spin. And as the coil's spinning, it turns the fan blades.
So the motor effect is basically turning electrical energy into mechanical energy,
Yeah.
making things spin and move.
Yeah.
That is so cool. I bet electric motors are used in loads of things apart from just fans, right?
Tons of things. Cars, washing machines, electric toothbrushes, even those tiny little vibrating motors you get in mobile phones.
Yeah, yeah.
They're everywhere.
They are the unsung heroes of the modern world,
Mm-hmm.
quietly converting electricity into motion. It's brilliant.
Yeah, absolutely.
It's incredible how something invisible, like a magnetic field, can create so much movement and power. I'm starting to see magnets everywhere now.
Yeah.
But is it always a one-way street? Can we go the other way? Can we use motion to create electricity?
Yeah, you can.
Really?
That's where electromagnetic induction comes in.
Electromagnetic induction. Okay.
So it's kind of like the motor effect in reverse.
All right, I'm intrigued. Tell me more. How does this work?
So imagine you've got a wire and you move it through a magnetic field.
Right.
That movement's going to create a voltage across the ends of the wire.
So just by moving a wire near
Yeah.
a magnet, we can create a voltage.
Yeah.
That's insane.
And if you connect the ends of the wire to make a complete circuit, you'll get a flow of electricity.
That is mind-blowing. So we can generate electricity simply by moving a wire near a magnet.
Absolutely.
That seems almost too good to be true.
Yeah.
And this is the fundamental principle behind how we generate electricity, like on a large scale.
Yeah, so with things like electric generators.
You mean like those huge generators that you see in power plants?
Yeah.
The ones that keep our lights on, that keep our phones charged. Tell me more about those. How do they work?
So imagine a coil of wire spinning rapidly
Okay.
inside a powerful magnetic field.
Yeah.
So as the coil spins, it's cutting through those magnetic field lines,
Mm-hmm.
and that's creating a voltage across the coil. And because the coil's spinning, the direction of the electricity is switching back and forth, so you're creating what's called alternating current. or AC.
Ah, so that's why the electricity that comes out of our wall sockets is AC.
Yeah.
It's all thanks to spinning coils of wire and magnets.
That's right.
That's pretty amazing. But hang on a minute. How do we control the voltage of the electricity generated? I mean, we need different voltages for different things, right?
Yeah.
My phone charger doesn't need the same amount of power as a washing machine.
That's a good point. That's where transformers come in?
Transformers, like those big metal boxes you see on power poles.
Yeah.
I always wondered what they were for.
Yeah, so they're like the voltage regulators of the electrical world.
Right, okay. So they can either like boost the voltage up or bring it down.
Exactly. So you've got step-up transformers.
Yeah.
They increase the voltage, and step-down transformers,
Right.
which decrease the voltage.
Okay, but how do they actually do that? How can they like manipulate the voltage like
Well,
that?
it all comes down to the number of coils of wire. So think of it like a seesaw.
Okay.
So on one side of the seesaw, you've got the primary coil. That's where the incoming electricity is flowing. And on the other side, you've got the secondary coil. That's where the outgoing electricity is flowing.
Okay. Yeah.
So if you want to increase the voltage, you need more coils on the secondary side.
So it's like having a bigger kid on one side of the seesaw.
Yeah, exactly. So more coils means a higher voltage, fewer coils means a lower voltage.
This is blowing my mind. So transformers allow us to like send electricity over really long distances at high voltages
Yeah.
to minimize energy loss
Yeah.
and then step it down to lower voltages that are safe for our homes.
Yeah, exactly. So transformers they're essential.
Wow, it's like this giant electrical balancing act.
It is. Yeah.
This deep dive is electrifying. We've covered so much ground here, from magnets and magnetic fields to motors to generators. It's amazing to think that it all basically boils down to the interaction between electricity and magnetism.
Yeah. Pretty amazing, isn't it? And we're not done yet.
Oh, I can't wait. What other electrifying wonders do you have up your sleeve?
Well, how about microphones and loudspeakers?
I have to admit, I haven't really given much thought to how those things work.
Right.
I kind of just assumed they were magic.
Yeah. Well, I mean, they do seem pretty magical, but the magic all comes from these principles of magnetism and electromagnetism we've been talking about. So, for example, a microphone that uses something called the generator effect to convert sound waves, which are just vibrations in the air, into electrical signals.
Hold on. So you're telling me that my voice can be turned into electricity?
Yeah.
Just like that?
Just like that. So remember how moving a wire through a magnetic field creates a voltage?
Yeah.
So microphones work on a similar principle.
Okay, I'm listening. Tell me how my voice gets turned into electricity then.
So inside a microphone, you've got a diaphragm. So this is a thin piece of material that vibrates when sound waves hit it.
Right.
So think of it like your eardrum.
Oh, okay. So it's like a mini eardrum catching all the vibrations.
Exactly that, yeah. And attached to the diaphragm is a coil of wire. And this coil sits inside a magnetic field.
Right.
So when you speak, your voice makes the diaphragm vibrate, which causes the coil to move back and forth within that magnetic field.
And that movement creates a voltage in the coil.
Yeah.
Just like with the generator.
Exactly. And the cool thing is that the voltage changes depending on how strong and how fast those sound waves are hitting the diaphragm. So your voice, with all its unique characteristics, creates its own unique electrical signal.
That is so wild. So my voice is literally like a pattern of electricity.
Yeah.
That's pretty amazing.
Yeah.
But how does a loudspeaker then take that electrical signal and turn it back into sound that we can hear?
So loudspeakers are kind of like the flip side of microphones.
Okay.
They use the motor effect to convert those electrical signals back into sound waves.
So we're back to electricity creating motion again.
Yeah, absolutely. So inside a loudspeaker, you've got an electromagnet, which is basically a coil of wire wrapped around a piece of iron.
Right.
And this electromagnet is connected to a cone-shaped diaphragm.
Like those big speakers you see at concerts.
Exactly, yeah. So when the electrical signal from a microphone or your music player reaches the loudspeaker, it makes the electromagnet interact with a permanent magnet, just like in an electric motor.
So the electromagnet starts like moving back and forth.
Yeah, exactly.
Yeah.
And as it moves, it pushes and pulls on the diaphragm, causing it to vibrate.
And those vibrations create the sound waves that we hear. That is brilliant.
It is, yeah.
So the next time I'm listening to my favorite tunes, I'm going to remember that it's all thanks to the interplay between sound, electricity, and magnetism.
Yeah.
I'll never look at my headphones the same way again.
Yeah.
This whole deep dive has been absolutely electrifying. We've covered so much ground from the basics of magnets to
Mhm.
like the complexities of generators and transformers, and now even microphones and loudspeakers.
Yeah.
It's amazing to see how all these principles are at work all around us. But before we wrap up, I have a question.
Yeah.
What does all this mean for me? Why should I care about magnets and electromagnetism?
Well, that's a great question. And the answer is that magnetism and electromagnetism are everywhere. They're not just like theoretical concepts,
Yeah.
in a textbook. They're the forces that power our modern world.
Okay, give me some examples. How do these forces actually affect my everyday life?
Well, think about all the things you use every day that rely on electricity. So your phone, your computer, your lights, games consoles, the electricity that powers these devices, that's all generated using electromagnetic induction in power plants. And then transformers, they help to transport that electricity over long distances and bring it safely into our homes.
Right. And then you've got all the things that actually use electric motors. So cars, trains, washing machines, even the tiny motors in your phone that make it vibrate.
Absolutely. And it's not just gadgets and appliances. The Earth's magnetic field, which we talked about earlier, that's created by the movement of molten iron in the Earth's core. And that magnetic field actually acts as a shield,
Right.
protecting us from harmful radiation from the sun.
Wow, I never realized how crucial magnets and electromagnetism were to our very existence.
Yeah. It's easy to take them for granted, I think,
Yeah.
because we can't see them. But yeah, they really are fundamental to the way our world works.
I'm feeling so much more aware of all these invisible forces at play now.
Yeah, good.
I want to go out and look at the world with new eyes.
That's the spirit.
Well, before we say goodbye, do you have any final thoughts for our listeners to ponder?
Sure.
Maybe something to kind of keep their brains buzzing even after the episode is over.
Well, we've talked about a lot of devices that rely on magnets and electromagnetism, but I'm sure there are many, many more. So I guess the challenge is think about your everyday life, your home, your school, the world around you. What other devices can you think of that use these principles of magnetism and electromagnetism? I bet you'll be surprised by how many you can find.
That's a great challenge.
Yeah.
I'm going to start brainstorming right away. And listeners, be sure to share your discoveries with us on social media. We'd love to hear what you come up with.
Yeah, absolutely. Keep those brains sparking. And never stop exploring.
Well said. And on that note, it's time to power down this deep dive. Thanks for joining us on this electrifying journey.
Cheers.
Until next time, keep those minds curious. So we've really been on quite a journey with this deep dive, haven't we?
We have, yeah.
I mean, from the tiniest magnets to like the Earth itself acting as one giant magnet.
Yeah. It is amazing, isn't it, how these things are working all around us.
It's incredible. So before we sign off, I thought it would be good to kind of recap all the key things that we've learned.
Okay. Yeah, good idea.
Where should we start?
Well, I guess we started off with those bar magnets,
Yeah.
with their north and south poles.
Yeah.
And how they attract or repel,
Yeah.
depending on which way you point them.
Exactly. And those invisible magnetic fields that surround every single magnet.
Right.
Getting weaker the further away you get.
Yeah. We even saw those iron filings
Yeah.
making those cool patterns.
They're so cool. And then remember how some materials like iron or nickel can become temporary magnets when they're near a permanent magnet?
Yeah, that's right. Yeah. Induced magnetism.
Induced magnetism. Yeah, we learned a new word.
We did.
Oh, and how can we forget the fact that the Earth itself is a giant magnet
Yeah.
with its own magnetic field generated by the molten iron core,
It's right. Yeah.
which is why compasses work, always pointing north.
Absolutely.
Yeah. And then we went on to talk about the really fascinating relationship between electricity and magnetism.
Yeah. And discovered how electricity flowing through a wire creates its own magnetic field.
Yeah, the right-hand grip rule was a game changer. I could suddenly visualize the direction of the magnetic field. I felt like I was doing magic.
Yeah. It's a good trick.
And then those coiled wires, solenoids that create even stronger magnetic fields. I mean, they're used in everything from doorbells to MRI machines.
Yeah, lots of applications.
It's amazing. And then we got onto like the really cool stuff, the motor effect.
Yeah, the motor effect.
Who knew that putting a live wire near a magnet could actually make it move?
Yeah, I know it sounds crazy, but it's true.
It's incredible. And that principle, of course, is what makes electric motors work.
Yeah.
And electric motors power just countless devices from cars to washing machines to electric toothbrushes. I mean, the list is endless.
Absolutely, yeah. They're everywhere.
And then, of course, we can't forget about electromagnetic induction, which is kind of like the motor effect in reverse. That's how generators create electricity
Yeah.
by moving a coil of wire through a magnetic field.
That's right, yeah.
And then transformers, those clever devices that they can increase or decrease the voltage of electricity, which
Yeah.
is essential for being able to send it over long distances
Yeah, absolutely.
and to make it safe for use in our homes.
Yeah.
We even touch upon how microphones and loudspeakers use these same principles to convert sound waves into electrical signals and back again,
Yep.
which is pretty amazing when you think about it.
It is.
It's
Yeah.
truly remarkable how intertwined magnetism and electromagnetism are with our everyday lives. You know, from the power grid that keeps our lights on to the headphones that let us enjoy our favorite music. These forces are literally working tirelessly behind the scenes.
Yeah, absolutely.
I feel like I've gained like a whole new appreciation for these concepts.
Yeah.
It's like I'm seeing the world with X-ray vision now. You know, understanding all these invisible forces that are at play all around us.
Yeah. And that's just the tip of the iceberg, really.
I know.
There's so much more to explore out there.
Absolutely. Well, I want to thank you so much for being such a fantastic guide on this deep dive. You've really demystified these complex concepts and made them so accessible and engaging for everyone. So thank you.
You're welcome. It's been a pleasure.
And to all our listeners out there, keep asking questions, keep exploring, and never stop being curious about the world around you.
Absolutely, yeah.
That's a wrap on our deep dive into magnetism and electromagnetism.
Great stuff.
I hope you've enjoyed the journey as much as we have. Until next time, keep those brains buzzing.